We are starting on page 1 with acid-base indicators. And in general, oh yeah, they accidentally printed it in color, which is like really good because it's all about indicators. So it's like super exciting. Anyway, yeah. And I checked, I did not select color because it's way more expensive, like thousands of times more expensive. Well, not thousands, but lots. So I'm like, well, not my fault. At any rate, indicators change color in the presence of other chemicals. So in our solubility unit, we had the chromate ion, which changed to a red color in the presence of silver. Do you remember that one? Yes. Okay. In this unit, we are specifically looking at acid-base indicators. And acid-base indicators, it is the weak conjugate acid-base pair. It's not just one of them, it's both of them together. So you have the protonated form with the proton, so we have the H, and we have the unprotonated form that is missing an H. And they each have different colors. So we have one color and we have a different color. And so basically it would be the HIN and IN minus make the indicator. Now, what is with this IN business? It's just short for indicator because indicators have very, very complicated formulas. So we'll just often say, oh, we'll just call it IN for indicator. Now, every different indicator changes color at specific pHs or pH ranges. Okay? And in fact, if you would like to get out your data booklet, and go to page 7, you can see that each indicator will change color between a certain pH range. So for example, phenolphthalein, which we used in our titration lab, changes from 8.2 to 10.0. So below pH 8.2, it is colorless. Above pH 10, it is pink. In between the two, it would be that pale pink color that you were striving for. Okay? Now you're going to see why we use HIN and IN minus, because this is the actual chemical structure of a particular indicator. Très, très compliqué, yes? So we don't really want to do too much with that. What we do want to notice with our structure is that these two chemical species are identical, except this one has an H and this one has no H. All right, so we have our acid form of the indicator, which has the H on it, and it is the color yellow. And we have the BG form. We've called it BG for brom-cresol green. Okay, you could call it HIN also. And the BG minus form of the indicator, the base form, is blue. And this is just explaining that we might pick a specific way to reference it. So since this is Brom-Cresol green, we called it HBG. But if you don't want to go that far, you can just call it HIN or HIND for indicator. Okay. So this is just, again, stressing that the indicator is not a single species. It is a mixture of both members of the conjugate acid-base pair. So Brom-Cresol green is actually an equilibrium mixture of HBG and BG minus. Brom-Cresol green is not just HBG. Both members of the conjugate acid-base pair must be weak so that we can get an equilibrium. We have to have an equilibrium because it needs to be able to shift from one side, which is one color, to the other side, which is a different color. So what's an indicator? It is a weak conjugate acid-base pair where one member of the pair is one color and the other member is a different color. So here's Brom-Cresol green. We have the acid form of the indicator, which was yellow, and we have the base form of the indicator, which is blue. Now let's say that we have an acidic solution. So this might be, for example, some HCl. This is actually very much like the common ion effect in the solubility, in that our indicator equilibrium contains the H+ ion. What does HCl contain? Contains the H+ ion. So if we have an acidic solution, that means our H+ concentration is high. And if it is high, what happens to our equilibrium mixture? It shifts to the left. So the position of the equilibrium is more to the left. So in acidic solution, concentration of H+ is high, and therefore it shifts to the left. And that means if it shifts to the left, what do we know about our HBG, our yellow form? HBG concentration will be, we've shifted to the left. High, yeah. And the BG, which is blue, will be low, yes. So we can say out of those two things, which one is the predominant species? Remember, predominant means main species present. Which one is mostly present? HBG. And if HBG is the main species present, the overall color of the solution will be yellow. Why is Brom-Cresol green blue in basic solution? What do we have a lot of in basic solution? Basic solution, we have lots of OH minus. And if we look at our equilibrium here, how is OH minus going to affect this equilibrium? Yeah, the OH minus reacts with the H plus, causing concentration of H plus to decrease. And if our concentration of H plus decreases, which way do we shift? We shift to the right, making the concentration of HBG, it will be low, and the concentration of BG minus will be high. I'm going to color code again here just for completion's sake. So we have lots of the BG minus and not very much of the HBG. Therefore, who is the main species? BG minus is the main species. What is the word meaning main? Predominant. And therefore, the overall color of the solution will be blue. Excellent. Now, as the equilibrium is shifting, like let's say that we started out in an acid solution, so we had mostly yellow, and then we started adding some base. Yes? We're going to, if we start adding base, we're going to eventually start shifting this way. So we're going to be taking some of our yellow and turning it into blue. All right? Now, at some point, we're going to have some yellow and some blue. So we'll have some acid form and some of the base form. So we will have some yellow and we will have some blue. And at some point, they are going to have similar concentrations. So when they transition, that is when the HBG and the BG minus concentrations are similar. Okay? What color would bromcresol green be when it is transitioning, when the concentration of the HBG and BG minus are similar? It's going to be green because yellow plus blue gives us green. That's why it's called bromcresol green. Yes. Some of them make sense. Some of them make no sense, right? Like you're like methyl violet is like blue and yellow and you're like, I don't understand. Should be red and blue, but whatever. Now, just so that you all remember your color combinations, yellow plus blue gives green. What does yellow plus red give? Orange. And how about red plus blue? Purple. And the reason I'm going through this is that every year there's at least one or two people whose kindergarten teacher dropped the ball and they did not teach them color combinations. So if you didn't know them, don't be ashamed. Happens every year. Now you know. All right, now, as the reaction is shifting, there will come a point at which the acid form, the HBG form, is exactly equal to the base concentration of the base form, BG minus. And that point is called the transition point. It is the point when color A is equal to color B. So it is the point when HIND concentration is equal to IND minus concentration, and that is the definition of the transition point. Now it's kind of cool because the fact that HIND and IND, or that should be a D there, IND minus. I need to fix that. Not that it really matters that much, but just to be consistent. It's kind of cool. So let's watch this. We have our indicator. We have our equilibrium for our indicator, HIND, H plus, IND minus, and we can write a Ka expression. Products, H plus, IND minus over reactants, HIND. Now, we know that at the transition point, IND minus is equal to HIND. And that's at the transition point. And if those two concentrations are equal, what can we do with them? Cancel them out. If one was 2 molar, the other would be 2 molar. Okay, they'll probably be a lot smaller than that, but that gives us the general idea. And then what are we left with? Ka is equal to H plus. So Ka of the indicator is equal to H plus at the transition point. Yeah? Now, if I was to take the negative log of the Ka, and if I was to take the negative log of the H plus, what do I get if I take negative log of H plus? I get pH. So, and what do I get if I take negative log of Ka? pKa. So pKa of the indicator is equal to the pH at the transition point. Now, at some point, I'm going to get really tired of writing transition point. So we're going to start abbreviating it as TP. Okay? Now, the fact that Ka is equal to H of the indicator is equal to H plus at the transition point will allow us to do 2 things. Number 1, if we are given the Ka, you can find the pH at the transition point. Because you know that if you know the Ka of the indicator, you know the H plus at the transition point, and from there you can convert it to the pH at the transition point. Is good? Okay. Also, if you are given the pH at the transition point, and I need to fix this and make it bold. You can find the Ka of the indicator. Because if you know the pH at the transition point, you can convert that to H plus concentration, and that is just equal to the Ka of the indicator. Now, on page 7 of your data booklet, we have the indicator, we have the pH range, and we have the color change. So we're going to, I've actually snagged the very first thing here. We have methyl violet, and it changes color pH 0.0 to 1.6, and it changes from yellow to blue. Okay, and we would like to know what is the pH at the transition point for methyl violet. So if we were to draw out our pH scale, we would see that at 1.6 or higher, okay, so at 1.6 or higher, it's going to be blue. And our predominant species is the base form, the MV minus. Now at pH 0 and below, it is going to be Yellow. Now, in between 0 and 1.6, what color will it be? It will be green, because you have a mix of both yellow and blue. No, isn't that annoying? Right? This is one of the ones where I'm like, sometimes their names are stupid. Like, why is methyl violet between yellow and blue? Makes no sense. It should be between red and blue, but it's not. Anyway, we don't use it very much because it changes pH at such a, changes color at such a low pH. It's not actually that useful. Now, our actual transition point is right in the middle of that range. How are you going to find the midpoint between 0 and 1.6? You're going to average them. So basically, you just take your 0 and your 1.6 and you divide 0.2 by 2 and you get 0.8. And that is the pH at the transition point. So we can find the pH at the transition point by averaging the two numbers at the end of the pH range of the color change. Now, everything is written out for you here, so I'm actually going to bop on over to the side. What is the Ka of methyl violet? And we know that the pH range was 0.0 to 1.6, and that means that the pH at the transition point was 0.0 plus 1.6 divided by 2 is equal to 0.8. Could you get to the Ka? What would you have to do to your pH? You would have to take to pH and change it into H. And then you would have to take your H. And what do you know about H at the transition point? It is equal to Ka. So that's pretty straightforward, yes? How do we go from pH to H? Tell your partner. Do you remember how to do that? Antilog. Antilog. It's the antilog of the negative pH. What's another way of writing that?
10 to the negative pH.
Yes. So we can take 10 to the negative 0.8. And we get 0.158. Now that would be molar because it is a concentration, but we don't actually want hydrogen ion concentration. We want the Ka, and the Ka is equal to concentration of H plus at the transition point. So that's going to be equal to 0.158, and we're going to drop the molar because now it's a Ka value and does not have a unit. What do you guys think about my sig figs?
There are too many.
There are too many. Yes? So remember when we have a pH, only numbers after the decimal count. So how many sig figs? 1 sig fig. So this should become 0.2. Or if we want to write it like most Ka values we see, we would call it 2 times 10 to the minus 1. Is that a strongish weak acid or is it a weakish weak acid?
It's a strong-ish weak acid.
How do you know?
It is high.
Ka is high, and therefore it is a strongish weak acid. Yes? Just reviewing a few little concepts here, right? From the acid-base 1 stuff. Having gone through that, you can probably do the example on the next page. Do you want to try that one on your own? Example 7, I think it is. And if you finish example 7, you can challenge yourself and see if you can figure out example 8 without.
Example 8. Unknown indicator is 3.8.
Well, you can also try example 7 first.
Oh, okay.
Do example 7 first, and then do example 8.
Wasn't count that any. Oh. Okay.
Oh, she might have emailed. I know, there's like this little symbiotic loop back there.
This is apples.
Not worry if you got me from.
If someone texted me out of nowhere not having famous, I'm just all.
If your sibling texts your younger sibling, it's terrifying. So it's very often.
I don't know.
I think most of you have mostly successfully done that. I'm just gonna let you check your work. And remember, if you're doing it for a quiz or a test, you always want to tell me what you are solving for, right? So you don't just want to throw those numbers up there without telling me, I am finding pH at the transition point, Ms. Spence. And now I am finding H plus at the transition point. And now I am finding Ka of the indicator. What do you guys think of my final answer? Wrong sig figs. How many sig figs should I have? Just one, because we got one number after the decimal in the pH. One sig fig, so that's going to become 5 times 10 to the negative 8. Do you guys want to try number 8 on your own?
Yes.
Yes? Okay. If you're stuck, call me over. Okay?
Did you find out where to take this?
No, nobody's coming back.
Oh, well, that's all what you're doing. What? What? You know, you. Let us cry. What? We just be involved in something.
Purple. Yeah, yeah, good.
By the way, this is unknown. You're not gonna find it on the phone. Okay, so.
Now when it changes the color, what do we call that?
Oh, that's stupid.
That's our transition point. So you're looking for the pH at the transition.
Okay.
Yeah? So if you're getting stuck on part B, what I want you to remember is that what do we call the point at which the indicator changes color?
Transition.
That is the transition point. So you are looking for the pH at the transition point.
That's the one we got. No. If I was pH by taking the negative log of H.
So that basic. And if it is basic, live there.
Oh. Yeah, I think this is.
Yes, yes. Yeah. So
Strong. What? When I was a kid, I used to eat butter toast, bro.
I meant a whole stick of butter.
Yeah.
$6 butter stick.
So when my mom, when my mom came, my mom would feed her this was butter, and I thought it was disgusting. Yeah. That's okay. It's fine. Yep. Good luck.
It didn't mention.
What am I doing? I'm sorry, I don't know what's wrong with me. I'm just, I'm doing. Yes. Yes.
I'm wearing contact.
Okay, my friends, I want to ask you a question here. There's a couple of ways of showing the work for this. You can say my pH at the transition point is equal to pKa at the transition point, and my pKa at the transition, the pK, or why am I saying at the transition point? The pKa is the pKa. Got excited about that. Okay. The pKa is equal to the negative of the log of Ka. So we have the negative log of 3.2 times 10 to the minus 5. How many digits should I have in this answer?
Oh.
Because my number is 4.49485. How many sig figs here? 2 sig figs. So how many digits should I have over here? 3, because I need to have 2 after the decimal place. Now, that's one way of showing the work. Another way of showing the work would be to say that my hydrogen ion concentration is equal to the Ka of the indicator. So now I know the Ka. So my pH is equal to the negative log, which is equal to 4.49. Same thing. Okay, now, what color is the indicator in 1.0 times 10 to the minus 6 molar HCl? Well, the easiest way to do this is to say, what is the pH of the HCl solution? Now, when you are given an acid and asked for its pH, what should you always ask yourself? Is the acid strong or weak? Is HCl strong or weak? Strong. And therefore, hydrogen is equal to HCl because it dissociates completely. So our pH is simply negative log of 1 times 10 to the minus 6, which is 6.00. 2 sig figs here, 2 sig figs here. Now, if we look at our indicator, we decided that our pH at the transition point was 4.49. And above pH 4.49, we have the base form, which is blue, because we are told up here the base form is blue. So when we have the higher pH, we get the base form, which is blue. And below, we get the acid form, which is red. So at pH 6, which is over here, we will have, the indicator will be what color? Blue. And who is the predominant form? The IND minus is good. You could write the base form. You could say base form if you wanted to. That would also be fine. Is good? Okay. All right, one last note. As we go down the acid-base indicator chart, the pH at the transition point, what's happening to the pH of the transition point as we go down? It increases. What does that mean about our Ka value? pKa rather. pKa, which is equal to pH, also increases. And if pKa is increasing, what's happening to Ka? It's decreasing. So, therefore, let's calculate our pKa and our Ka for methyl violet. We actually did that one already. It was 0.8 and 2 times 10 to the minus 1. Let's calculate our pKa and Ka for indigo carmine, which if anyone ever wants to name their child indigo carmine, I would think that would be really cool. And you should see if you can get in contact with me and let Uni know that you did that, because I would be like, oh, that is the coolest thing ever. But anyway, I don't expect it to ever happen, but I could see that actually.
I feel like if I ever had that before. And you Carmine, get over here.
Well, you don't have to call them by their middle name as well. Although I suppose if you're yelling at them, sometimes you do call people by their middle name also. Yeah. Indigo Carmine?
See, I almost have I said that this one, I'm almost
So what is happening to our indicators as we go from the top of the chart to the bottom of the chart? These guys up here are stronger acids. These guys down here are weaker acids. But remember, indicators are not just the acid form, they are also the base form. So up at the top, we have the stronger acid, we have the weaker base. And we have the weaker acids at the bottom and the stronger base down at the bottom. There are some exercises here, which I'm going to let you do after your quiz tomorrow. And we're going to move on to 5.1b. If you would like a 3-minute break, we could take a 3-minute break. Would you like a 3-minute break? Yes, you should go outside. Because it's nice out. Enjoy the sunshine for like 3 to 5 minutes. Okay?
Do it.
She said. What's that? How do we stop feeling? Stop feeling. Stop feeling.
What? Look at her.
How'd you get that? I'm just kidding.
Is it looking or just?
I fucking looked at the screen. That's how I
Is it no? You just take the negative mark. No, you do take the negative. Yeah, you just take it. Well, that ought to be it. Yeah, that's what it was. Oh my. Where's the light? You buy nice.
I usually all we can do it today.
It's fine.
We're asking all three more interactive.
Where we buy it. And one time buying shit off.
I have a confidence and put new ones in today more than
Oh wow! How was it freaking out?
Ask us what's wait, no. Got it.
It's fine. Things could be worse. I could be trying to do it.
Make sure you stick to your book. I always Windows locked and everything.
Is it cool to be all over? All that? Yeah, what's it?
You smell smell.
No, I smell what food. I don't know what. I smell a food. I don't know what it is. It's food.
Your nostrils.
I'm smelling some food. It smells good. It smells like barbecue or whatever it is. Look at your feet.
Is it cheese? Because we got cheese in our last block.
What?
You guys didn't get cheese in your last block?
We were looking at Evelyn. There's Evelyn.
Oh.
I got garlic cheese fries.
Whoa. Aren't you lucky?
Oh,
Did you guys want cheese?
I'm okay.
Like they're like the string cheese.
I'm not gonna lie. My hands are quite gross.
I'm good.
Okay.
It's like wrap. It's like the fun is the same break.
I'm not.
That's fair.
I'm not lying. My hands are dirty.
There's a sink right there. Like I'll have cheese on a cracker, but I don't think I'm a big cheese musher as a whole.
Like honest.
You just haven't had good cheese.
I'm
What about like brie?
I'm not a big like the brie on bread. Those you want to eat so good. Hot sandwich brie with hair on bread. So good and honey. Yes. Oh, the dining for.
I always do make the cheese.
You're disgusting.
No, it's good. Have you not?
I did, but like I don't want processed cheese with my processed strawberries. So
It's already processed anyway. So it's fine.
so like if I like give it a sandwich twice in a row, and it's on you know that.
No.
That's basically
No.
what
Because what's going on is
I was gonna see it.
you have to
I'm not gonna use it.
you have to process ramen, right? Which is already damage to your body. You have to process cheese, which is already damage to your body. It doesn't matter because at the end it's going to go down the right anyway. So that's throw it in combo.
Okay, so go
So
right
it's
back.
like-
Go back. We'll come to HCL and come back.
Okay, well, seriously, right? Cheese is
It's gonna
cheese
be
is
all you have.
So cheese is edible, and grabbing a chemical from in there.
Okay, I'm gonna give you actual edibles, like edible edibles, and like
Okay,
you
so
take
that-
two. one that's in
Okay, so,
because they're both
okay, so that's
positive.
different, because that's the case where it's like, to actually show that we're just making a bigger one.
That's the point, because 1 plus 1 is 2, and 2 is bigger than 1. That's what I'm trying to get over to you.
One-
No wonder you can draw calculus.
One drop of water, so the drop of water with a bigger drop of water.
What are you, King John?
Yes.
What?
Okay, it's been 5 minutes. So we're going to go to page 10.
I gave you some
And we're going to look at using acid-base indicators. Page 10. All right, so we have a solution now, and it turns phenolphthalein pink and it turns indigo carmine blue. Thank you. Coco Land.
Oh my god.
So pH is between 10 and 11.
Okay, so first of all, I want to explain how this works because sometimes people have difficulty visualizing this. If you have no problem visualizing it, you don't need to draw this, but you start with a solution. Yes, here's our solution. And we want to know its pH. We're like, what is its pH? So we take a sample of it and we put it into a test tube. And here's our little sample. Okay, and we add some phenolphthalein. And it turns pink. Now we take a second sample. And we put it into a different test tube. And we put some indigo carmine in it, and it turns blue. Okay, so what we need to do then is we need to look at our phenolphthalein and its color range. And we say, all right, I know that phenolphthalein is colorless below 8.2, and it is pink above pH 10. And since it is pink, we know the pH must be greater than 10.0. And if I don't care if you put greater than or equal to, it just really doesn't matter because I'm never going to ask you like I'm never going to ask you like what color is phenolphthalein at pH 10? And you're going to have to decide, oh, is it pale pink or is it pink? Like, I'm not going to ask you that because it's a stupid question. Yes? Yeah. Yes. Okay. Now, indigo carmine is blue. So what does that tell us? Indigo carmine is blue when we are below pH 11.4. So we know the pH must be below 11.4. So we can say there are two ways of writing the range of this solution. We can say pH is greater than 10.0, but it is less than 11.4. The other way to write it is that the pH is equal to somewhere between 10.0 to 11.4. Okay? So those are two different ways of writing the range. Does it matter that one of these ways of expressing the range includes 10.0 and 11.4 and the other says greater than 10.0 and less than 11.10? No, it doesn't matter. Blah, blah, blah. Okay? I will never ask you what is the color of indigo carmine at pH 13, where it changes, like where it's coming out of its transition zone. I will never ask that. All right, here are some other examples. You might also be asked to find the color of an indicator in various solutions, which will require you to remember all your tools from acid base 1. Yes? So if I say we have Brom Cresol green, and it changes from pH 3.8 to 5.4 from yellow to blue, if our hydrogen ion concentration is 1.9 times 10 to the minus 11, what color will Brom Cresol green be? I bet you guys could do that one. Did you guys get 10.72? Okay. And at pH 10.72, what color would Brom Cresol green be? It would be blue because we're above 5.4. Now for the next one, you are given a POH. Do you remember how pH and POH relate to one another?
They both equal or you have room temperature.
No, they don't.
Some of it.
The sum of them, not they both equal 14. pH plus POH is equal to pKW, which is equal to 14. So your pH would be 14 minus 7.8. 6.2. So Brom Cresol green would still be blue. And the reason I put this one in, we've got pH 4.0. What color will it be? It's going to be green. I don't ever want you getting fussed up about, oh, is it a yellowy green or is it a bluey green? No. Green is good. If you're in between those two things, I don't care if it's close to this end or close to that end, just call it green. Makes your life easy, okay? And this is where I got to with my other block. Wow. How did we do that so fast? Even with the break? Huh? Doesn't it? 14 minus 7.8? Yeah. We're good? Okay. So we're done. I don't know how we finished so fast. Basically, the next part is just like, if you're given an acid solution, you have to remember to ask yourself, is it strong or is it weak? If it's weak, what tools do you need to use? Rice and Ka. Yes. Okay. Anyway, we're going to leave it there for today because I don't see any point in rushing ahead. Okay. Your homework is your study for your quiz. After your quiz, you will have homework on indicators. So if you're like, I feel like I've studied for my quiz, you could work on pages 6 and 7 and 8 if you want to, and 9. That'll be for after your quiz. Okay? Or if you just want to chill, chilling's good too.
That sounds good. That's the thing. Sounds like
There.
no. Okay. You know what? It's too chemistry. Ice cream and oil are not mixable. Therefore, they will not combine. Mixable.
But cream is non-polar and so is oil.
Oh, Okay.
Yeah.
Never mind. Never mind.
You thought you knew that. That's a fair.
Whatever, Dr.
As if after that, I would go. Yeah. Really, you don't know me.
Okay, wow, I'm in the school. No, like,
Well, why did you do that?
but you're putting us in ice cream. What are we doing?
Jonathan.
What would you?
Brainwashed. But it looks good. No, it doesn't. How is white and green and gold? Unless you're looking at snow. Edible though. Yeah.
So let's grab that one. Equilibrium, equilibrium. There is solubility. Solubility. There you go. And so I think it says worked examples. Yeah.
Like big back, big back, big back.
I will get back.
And did everyone get a review for the units?
No.
If you were away last night. For the units. It's also on, yeah.
Oh, wow, thank you.
Oh, right.
Because you're out, you say, oh, what is this?